Morning. Sorry about my webcam here isn't working perfect, so my preview is not sticking itself in the corner there lately. And I haven't really figured it out yet, but they did an update. There's a power outage, so I think I have to do some reinstalling. And because the way the school division does the computers, they're not wide open. I can't reinstall things myself. So we'll see what happens in the next few days. If I can get that back. We're going to be looking at, in day 8, we're going to be looking at, in day 7, we looked at EMR theory, electromagnetic radiation, what an electromagnetic radiation wave was, and proposed by Maxwell. And then we looked at the speed of light being a constant in every single frame of reference, which led us into a little bit about special relativity. Today, we're going to do a couple of things only. We're going to look at emission spectra from atoms, which is kind of like the beginnings, and then Planck's constant, Planck's theories, which is kind of like the beginnings of quantum theory. Okay, so this is day 8 of Unit 4. And we're going to be looking at the spectra lines from elements, atoms if you like. We're going to be looking at basically the 3 kinds. Okay, and kind of what the differences are in there. And then we're going to be looking at Planck's Planck's quantum hypothesis. We'll call it his idea, and there's a simple formula that goes with that. Okay, and that's what we're going to kind of look at today in physics. Just going to pause here and answer an email real quick here. It's early in the morning, so we'll get right back to it in a minute. Okay, so the first thing we're going to look at is spectral lines and what they were and why they were important in modern physics. The first thing is a little bit of history here. Spectra basically is one of the major keys to understanding the structure of atoms. Okay, because what they were finding is when they took gases of an element and they passed, light through it, white light or different kinds of light, they could come up with different spectral lines would come out on it as it went through. They would use a diffraction grating or a prism, and they would see these lines, spectral lines. So first thing I'm going to do is I'm going to describe what spectra are, and I'm going to describe the 3 kinds that exist in nature. Okay, so spectra lines are, so the first kind that we're going to look at is something called continuous spectral lines. Oops. Okay, so now these were basically produced when light from a glowing solid or liquid passes through diffraction grating. Okay, so Okay, passes through a diffraction or prism. Okay. Continuous spectra, the light is of all colors or all frequencies of light. They just flow into the next. Okay. The spectrum shows all colors of light. And they flow each other. Okay. So this is produced with, let's draw a picture. This is produced with, this is, you've got over here, oops, got to get my marker set up. A glowing solid, object or liquid, depending on what it is. Okay, and it's producing light, and this white light kind of comes out here like this. We have okay, comes up to a diffraction grating or a prism. Let's just draw a prism here. Okay, and then it splits based on kind of it diffracts here. Okay, this one will go. This one bends a little more. And what we see over here is our spectral lines. Okay, let's draw this better. Okay, so you're going to see your red, okay, let's got to get my colors out here. Orange and yellow. And then green. And we got some blue. And then we got some violet, or indigo and violet, if you remember from our, and then back here we got some violet. This one here. Okay, so we've got our spectral lines. They're all continuous there. This is kind of what we're used to seeing. They're all nice and continuous. They flow into each other. They're nice and smooth. Continuous spectra. Okay, they all nicely flow into each other and split up real nice, see the whole rainbow effect kind of thing. Okay, and we've seen that before. Okay, and that happens with the glowing solid or liquid. Okay, what they found though, as they did some research and were looking at things, is B. They had some bright line spectra of different elements. Now, what bright line spectra are these are when you took a gas of an element or compound like neon gas or hydrogen gas or something like that, and you excited the gas, okay, they got it moving around and high energy, and then you passed, I think it's a white light, let me just check here. Oh no, you just passed the gas from this excited, or the light that was produced from this excited gas when you excited it through the diffraction. What you ended up getting was bright line spectra. Okay, so it's kind of something like this. Okay, you have a, I guess we should kind of keep to the same format. Okay, so the light from an excited gas, it's not a solid or liquid anymore, is passed through the prism or grating, and bright line spectra forming, I guess is a better word. Oh boy, there we go, finally got it. Forming bright line spectra. Okay, and the bright line spectra, there's only light at certain frequencies. These spectra lines show light at certain frequencies only. And where they were located in there, they used this actually to help identify elements, because then you had hydrogen there, it would have certain bright line colored spectra in certain spots. Rather than the whole continuous spectrum, you would just have little strips of color, and some colors would be missing. I'm just double checking here. It says this is about 18, let's see here. Every element produces a unique line spectrum. 1823. Okay. Okay. First guy that suggested that each element would be different was John Herschel. So that happened in about 1823, and it looks something like this. Let's draw it out here to bright line spectra. So we'll get the same format here. Okay, we draw our gas chain. Okay, so this would be where we have our excited gas. Okay, and then this light, it's not necessarily going to be white light this time. It's going to produce this light. And we got our spectrum splitter in here, prism or diffraction grating. Okay, that's just the light from gas. It's not necessarily That, and then what we would have over here is we'd have this coming in and giving us this the rainbow effect again. So come have a little bit of bend there, and okay, and on the wall or on the screen, we'd have our bright line spectra over here. So everything would be dark except for the lines. So it would be okay. So if I'm going to draw this, we're just going to draw it from like that would be right where the red is, that top arrow there. And then that would be where the violet is, where the bottom arrow is. So let's just kind of go in there. Okay, and this would be all dark. So we'll kind of shade it in dark. Except for certain places, there would be, a line, a bright colored line, like a yellow there, at a certain position. So it'd be all dark in here. Let's just color it in. We'll just go over top of it. So they wouldn't see any light in the spectrum. But they'd have like a yellow line there and maybe a green one here and maybe a violet one right now down here. Okay, and this would be a bright line spectra lines. Okay, so they were puzzled. Why was a solid or liquid giving you the light from that? Okay, that it's giving off. Why is that giving us a continuous, nice rainbow of all the spectrum? And then when we do light from a gas, bang, we've just got dark spots here, and then we got these bright spectral lines in the dark spots. Okay, so you would just see these small lines. Okay, so they weren't sure about that, and then that, like I said, that happened in the early 1800s, and this John Herschel guy said, "Hey, we can use this to identify particular elements." So, bright line spectra. Being different from continuous spectral lines. Confused the scientist. There was, or I guess, showed an anomaly. They needed to figure it out. Just one L in that, I guess. Okay. These can be used to identify elements. Characteristic. Property. Okay. In chemistry. Okay, so that's one of the things they did. Now the other and the last one we're going to look at is dark line spectra, but I'll do it on the next page. So it's basically the opposite of this one, where you would have the whole spectrum in here, and then you'd have some white splashes of light or dark lines blocking out certain areas, so not white light, dark lines. Pardon me. Okay, so let's go ahead and do that last one. Dark line spectra. That would be C. Okay, so dark line spectra here. Let's make sure I get it right here. It was it's produced the same way that continuous light spectra is produced. However, the light produced by the glowing solid or liquid, okay, passes through a gas. Okay, so they got an extra thing in the way. Okay, before it passes through the diffraction grating. Okay, in the dark line spectra, light of certain colors is missing from the spectrum. Okay, the solar spectrum is really a dark line spectrum. Dark line spectrum is called Fraunhofer lines. Ooh, I don't even know who Fraunhofer is. It's been a while since I've done spectral lines, but let's see. Let's not draw it. Let's first define it and then draw it. So this is basically, as they say, I guess we should put a C there because we keep it consistent. Okay, so these are produced when light from a glowing solid or liquid is passed through a gas, not excited, before passing through the prism or diffraction grating. And the result is resulting in dark lines in the continuous spectrum. Okay, spelled that wrong. Dark line spectra is called absorption spectra because that gas is absorbing those particular frequencies of light. Okay, so drawing it, it looks like this. We've got that extra area now. We've got this is our glowing gases or liquid. Sorry, solid or liquid. Okay, this is white light coming out. Okay, and then it passes through an unexcited gas. So we've got another chamber here. Okay, and then, it comes out of there. Oh, not that. I want my line tool. There we go. Okay, then it comes along and hits this diffraction grating or prism. splits into the continuous spectrum with dark lines in it. So here we have so what you're going to see now is dark line spectra. So you're going to still see that red, where we are here, red up here, orange, it's kind of a crappy orange, yellow, and these are all different frequencies of light or wavelengths of light if you like. Okay, green, blue, indigo, and violet. Okay, we're going to see that all nicely there. But in this time, certain spots are absorbed. So there'll be a black line there, maybe a black line here, and maybe a black line there. Okay? So this is where we get the dark line spectra. Okay? And this is white light here. Okay, before it goes into that unexcited gas. Okay? And what we do is dark line spectra is the only absorption spectra. Okay? So continuous and bright line spectra are emission spectra and dark line spectra are absorption spectra. Passing through that gas and it's absorbing certain wavelengths of light or frequencies of light. Okay, and that kind of, and these dark line or absorption spectra are they have a particular name. Okay, so they were wondering, why is it that it's not always continuous? Why does this happen? And the person that figured this out was Max Planck, and he proposed the quantum hypothesis that light comes out in packets of certain multiples or certain quanti. And that's where quantum physics started. Okay, and we'll talk about him a little bit here. I'm just going to pause and dig up my background on Max here, and then we'll get started on that, try to finish that up this period. Okay, so we're back here, and we're going to talk about Planck's quantum idea or hypothesis. Okay, so first I got to tell you a little bit about radiation of light and what actually happens or what's observed and what classical physics or classical mathematics and classical physics would say about it to predict it. So the first thing is the continuous spectrum of glowing solids or liquids. How does the intensity of light emitted from a glowing object or incandescent object, as they're called, how does the light emitted depend on the frequency? Okay, and that they were basically saying that what they were seeing was this. Okay, so if you took an incandescent object or what they call the black body, which is something that absorbed all frequencies of light and emitted all frequencies of light. Okay, so maybe I should define a few things first, and then I'll draw the picture. So black bodies objects emit, absorb, all frequencies of light. And that's what those are. What they were seeing, what classical physics said, okay, was they said something like this. As you took the intensity of the light, or the brightness of the light, and these are incandescent objects, okay, took the frequency of the light, okay, of the light, you should see a growing curve like that. The brightness of the light should go up as the increase in the frequency. Okay, I'll just read you a little piece here about incandescent objects, and then we'll compare it to what actually happens. It says, the ideal incandescent object is called a black body. Okay, it's a perfect radiator as well as a perfect absorber of all frequencies. According to classical physics, the radiation emitted from a black body is caused by the oscillation of atoms and molecules that make it up. So brightness is basically photons and all the element particles being emitted. Okay, and it says the spectrum analysis of the radiation emitted from a black body shows that the intensity of the radiation emitted depends on both the frequency of the radiation and the temperature of the object, as shown in the following graph. Okay, and I'll show you what that is right away. A mathematical relationship between intensity and frequency and temperature could not be developed, okay, using classical physics. According to classical physics, this graph should be described as below. Okay, the frequency. Okay, and this is what actually happens. So that was classical physics, and this is the observed graph. So I'll draw you the observed graph. Okay, so this is light intensity, or emitted radiation, if you like. Okay, and frequency. Okay, and what they saw was this kind of relationship. They go up, kind of hit a hill, come down like that. Okay, and then there was another one that happened at a lower temperature. This is at 3,000 kelvins, and this one was at 5,000 Ks. So 3,000 was where that peak happened for the first one, for that intensity, and if you had it at 5,000, you have more intensity of light, and then this would be at 5,000 Ks. So what was happening here is the intensity would go, and the frequency of light would go up, or the emissions. Okay, any electromagnetic radiation past the light spectrum or whatever, and the intensity would go down here. according to classical physics, it should keep going up. Okay, so they could not, we'll do it on the side here. So this is the observed phenomenon. Okay, and they saw that it was dependent on temperature as well, right? So classical physics do not explain the observed relation. And I'm getting into 36 minutes here. I'm going to kind of wrap this up in the next 3-4 minutes here. Okay, they cannot explain the observed relationship. Okay, so what Max Planck proposed was that any energy that was being emitted had to be emitted in quantized packets. And it's noted that this theory was not accepted. They laughed at this guy. They're like, that is stupid. He didn't even believe it himself, actually, the saying goes. It was such a radical idea. It's like saying that if you had a pendulum that was swinging, the energy of that pendulum wasn't continuous. It had to be in small packets of energy, so you could only have so much energy in there. Okay, so Max Planck then said, get this, before we run too far here, I don't want to go too far into it. Planck proposed the energy released was quantized. Quantized, I can't spell that like that. I think that's how you spell quantized. I'm not sure. Quant, I-Z-D-E, yeah, was quantized. Okay, that meaning only certain frequencies or multiples of energy. What do they say? Extremely. Let me just get the right word here. Okay, so only certain values they use, not multiples, of energy can be released. Okay. This was the beginning of quantum physics. Okay, so he had a little equation that he used, and then we'll stop there. The energy released is equal to NHF. Okay, this is energy. Okay, this is any whole number, so that's why I'm saying multiples. H is Planck's constant. So that's 6.63 times 10 to the 34 joules seconds. and F is the frequency of the vibration of the particles. Okay, and we'll look at this a little bit more tomorrow. Okay, so that's Planck's constant. So this means that it depended on the frequency and some whole number multiple, and so that there were certain values of energy that could not be obtained because it was quantized. Okay, and that's the beginning of quantum physics. Okay, we're going to be looking at a couple more things in quantum physics: photoelectric effect. I think there's that one there. We also have that. Okay, and then we'll look at maybe X-rays as well, and maybe a few other things, and that'll probably take us to the end. So we've probably got 3 or 4 days left. As you can see, most of the stuff is theoretical. Okay, so we're going to stop there today, and hopefully I'll get my camera fixed up before we do our next lesson.